Hi everyone, thanks for coming for my talk. Thanks Grigori for introducing my talk about performance. So for today we are going to talk about performance of our software. We like performance for the different reasons and we like optimize our software. Actually there are different ways about how our software can be optimized, different compiler optimizations can be applied to our applications and so on. And for today, I'm going to talk about one specific compiler optimization that can help you to optimize your software really, really well. Before the start, I wanted to show you some benchmarks. I applied profile guide optimization to many real-life software that probably are deployed in your production environment. And I got really, really impressive results, at least from my point of view. Here we see different applications from different domains: databases, compilers, web browsers, network proxies, log shipping solutions. And all of them can be, and performance all of them can be improved really, really nice. So at least for now, we know that PGO is not a theoretical thing. It's an optimization that works in practice. Few words about me. I used to be a C++ engineer. For now, I don't write code almost for 2 years. And when I need to write something, I use Rust instead, and I'm happy with that. I used to work as a part of International C++ Committee Working Group 21. If you know something about C++, I was working on some compile time-oriented stuff and numerics things. I also spent several years with hacking LLVM on different levels, front-end, optimization stuff, static analyzers, and so on. Not professionally, as a hobby, but at least I know something, not so deep, but you can expect some knowledge. And last year and a half, I spent with optimizing different applications with PGO almost on a daily basis. I collected a lot of experience with that. I collected almost all traps during my journey, and I want to share all of them with you. So let's take a quick look about how our build optimization pipeline usually looks like. There are two major ways about how our application can be compiled. The first one is the ahead of time school or AOT. We have a pretty simple CI/CD pipeline. Our source code is compiled by compiler, and then the resulting machine code is deployed to a target machine. The second way is just-in-time way, or JIT. The same CI/CD pipeline, the same source code, but as a result, we have some kind of bytecode or intermediate representation, and then this intermediate representation is deployed to a target machine, and on the target machine, we have some virtual machine, like an interpreter or like that, and this bytecode is executed on target machine. Modern compilers, good modern compilers, usually have inside a lot of optimizations that can help you to optimize your software. Like inlining, hot-cold code splitting, loop roll-and-rolling, LTO, some architecture-specific optimization, and so on. I'm not going to talk about them. All we need to understand that many of these optimizations can be really improved by providing some kind of runtime statistics to them. And here we have a problem, because in JIT world, we have a virtual machine on our target machine. And then we can collect some runtime statistics and recompile our software directly on a target machine. In AOT world, we don't have such a possibility because we don't have a compiler on a target machine. And profile guide optimization is a solution for this problem. What if we collect somehow runtime statistics about how our application is executed, which parts of our applications are executed, how frequently, and so on? Thus, this information to a compiler and then use this profile of our application during the compilation phase. That's it. That's all the idea. Let's take a look on a quick example. We have a simple function in C that checks an input variable of 3 numbers and the corresponding assembly to this function that compiled with a Clang, the most recent version, I guess, in the release mode. Pretty straightforward assembly. We just compare an input variable one by one. When we apply profile-guided optimization, the generated assembly is a bit different. The training workload for this optimization was a workload when the most frequent input for this function was the number 322. And the compiler decided to make a bit different optimization decisions. The most notable one is that the comparison with 322 number was moved to the beginning of the function. Why the compiler decided to do that? Because the idea is very simple. If we decide to, if the number 322 is the most frequent one, it makes sense to compare with it as early as possible, so we can achieve an early return. And that's why the return statement is also moved to the beginning of the function. It improves CPU instruction cache locality. It also improves performance of our application. And the rest of the program remains the same. So all called code was moved to the end of the function. There are different PGO kinds, actually. The most common one is a PGO via instrumentation. Some engineers decided to implement more advanced way to use PGO, that is called sampling PGO, and actually there are more advanced flavors and combinations between them. For example, context-sensitive intermediate representation PGO and different combinations. I'm not going to talk about them because they are quite exotic and experimental, and we don't have enough time, but I can talk about them after the talk. So let's start. How does instrumentation PGO work? At first, you need to compile your application in the instrumentation mode, run the instrumented binary on your target workload, or sometimes it's called a training workload, collect PGO profiles, and then recompile your application once again with these PGO profiles. That's all the idea. But what does instrumentation means in practice? Here we have another function in C language, a simple function that compares one input variable with a meaning of life, 42, and the corresponding assembly that also is compiled in the release mode. When we apply instrumentation for this function, the generated assembly is a bit different. The most notable change is that an additional instruction is inserted to our function. This instruction is inc quart ptr. It's automatically inserted by your compiler counter. It is automatically incremented each time when this function is called in your program. And when your program is finished, all counters from all your applications are saved to a disk in some file name. Since I use Clang, a LLVM-based compiler, we have some LLVM machinery here. As a default PGO profile name, we see here default.prof_raw and some machinery like LLVM profile raw version, because since it's a file, it has some format, it has some version, and so on. Unfortunately, instrumentation PGO has some caveats. At first, you need to compile your application at least twice. The first one during the instrumentation phase, and the second one during the optimization phase. And don't forget to run a training workload. So your CI pipeline will not be happy, since you need to compile your application at least twice, and it can be critical, especially for large applications like compilers, databases like ClickHouse, and something like that. An instrumented binary is larger because an additional amount of instructions are inserted to your application. And instrumented binary is slower because an additional amount of instructions is executed during the runtime. But how critical are these caveats in practice? I collected some numbers for, once again, real software. And as I would say that the binary size increase is not really critical in practice, especially if we are talking about modern servers, since we are not really disk limited. However, if you are working in some disk constrained domain, like an embedded domain, you need to keep in mind this binary size increase. Nothing too critical. You can expect usually up to 2x binary size increase. But if we are talking about binary size slowdown, the things become much, much worse. Unfortunately, instrumentation, PGO can, during the instrumentation phase, can introduce really, really big slowdown. For example, the first case about ClickHouse, the actual slowdown was more than 300 times. It's not a mistake. These numbers are confirmed with ClickHouse developers. Such a slowdown the reason for this slowdown was since instrumentation counters were inserted to really hot loops inside ClickHouse, and since these loops were executed during the training workload really frequently, that's why such slowdown was happening. For other applications, the actual slowdown sometimes less, sometimes worse. Like, for example, for Tarantul database, just not so critical, I would say. So also, the actual slowdown really depends on your software, how many branches does it have inside, and on your training workload. Google engineers, Google is the largest PGO user in the world right now, met all these problems, I guess, 10 years ago, and they decided to resolve them. And that's why they implemented a sampling PGO. How does sampling PGO work? At first, you need to run your usual application without any instrumentation. Almost usual because you need to insert some additional debug information for mapping, but it doesn't affect performance of your application. You need to collect runtime statistics about your execution, not via built-in counters into your application, but via an external profiler like a Linux perf for Intel vTune with a sampling-enabled product driver. You need to recompile your application once again with this runtime information, and that's it. That's all the idea. Unfortunately, sampling PGO also has caveats. The first one is called BSS, or branch stack sampling. It's a hardware feature that helps your profiler to sample, to collect runtime statistics about execution more efficiently and more precisely. In many instructions that you can find in the internet about PGO in compiler documentation, they recommend to enable BSS during the runtime statistics collection. Unfortunately, availability of this feature can be quite limited. For example, Intel calls this feature last branch record, or LBR, and it's available from, I would say, ancient CPUs, and the support was added to the Linux kernel many, many years ago. AMD calls this feature branch sampling, or BRS, and it's available since Zen 3 CPUs. For the ARM architecture, this feature is called branch record buffer extension, and it's available from the most recent ARM architecture specification. And regarding Linux kernel for the Linux perf support, I'm not sure that it's still mainlined. RISC-V, the feature is called control transfer records, and current status work in progress, nothing to try it. Elbrus, if you care, of course. The feature is supported on the hardware, but no support on the Linux kernel yet, even in some private versions, I would say. And if the most critical limitation here is that this feature, BSS or LBR, it's commonly called LBR, doesn't work with virtualization because, as far as I know, no hypervisor, modern hypervisor, emulate this feature properly. So if you know any software that does it, please let me know. And the second limitation, it's limited tooling support, because instrumentation PGO was implemented at least in GCC more than 20 years ago. And sampling PGO is a more modern technique, and it has some tooling problems. For C, C++, Rust, Fortran, the only options are two major projects. It's Google AutoFDO and LVM ProfGen. Let's start from the most commonly used, Google AutoFDO. Why do you need this tooling, this sampling PGO? When you collected runtime statistics from your application via an external profiler, you need to somehow convert from a profiler format to a compiler-compatible format, because your compiler doesn't know a format from your external profiler. They are different software. And Google implemented such a conversion tool. With Google AutoFDO, it's possible to convert a profile from a Linux peer format to a LLVM or GCC compatible format. Unfortunately, Google AutoFDO has many bugs inside, as usual Google tooling. It has many build issues with the most recent LLVM version. It has issues with memory consumption and so on. And unfortunately, these issues are not fixed for some reason. Hopefully, some of them will be resolved soon, since Google plans to contribute Google AutoFDO directly to the LLVM monorepository, and at least build issues will be resolved, I hope. Another tool is called LLVM ProfGen. This tool is already a part of LLVM project, so at least no build errors are expected here, but unfortunately, LLVM ProfGen doesn't work with profiles without BSS or LBR support. Google AutoFDO doesn't have such a limitation. By the way, in the internet, many people call sampling PGO as a FDO, feedback-driven optimization. AutoFDO exactly the reason why that's called so. For the Go compiler uses another infrastructure for doing PGO. It's called pprof, also a project from Google. I don't have a huge experience with PGO in Go for some reason. I'll talk about it later. But at least I tried it on several applications, and I would say it works quite well, at least in my case, with some limitations. So let's compare two different ways for doing PGO. At least, so instrumentation PGO allows to achieve better optimization. Once again, according to Google, sampling PGO usually can achieve from 80 to 90% of efficiency compared to instrumentation PGO. So if you aim to the peak performance, you need to start with instrumentation at first. Sampling PGO has far less runtime overhead compared to instrumentation PGO. For example, somewhere 2% of sampling PGO overhead compared to plus infinity instrumentation. Remember ClickHouse case. And even this amount of overhead can be tweaked via configuring a sampling rate. If you want to collect more precise and more efficient PGO profiles, you can increase sampling rate in your profiler. If you want to reduce an overhead in runtime, you can reduce sampling rate. That's a trade-off. And instrumentation has better OS and tooling support, because instrumentation PGO is implemented in all major compilers for different operating systems: Clang, GCC, MSVC, AOCC, Intel compilers, all of them support instrumentation PGO. If sampling PGO support is worse, since Google is the inventor, is the largest user of sampling PGO, they actually only care about Linux platform, and that's why they invest their resources into the Linux platform. So let's discuss some common PGO traps and mitigations for them. At first, PGO optimizes some cases and pessimizes others. Since we have a training workload during the optimization phase, that's obvious that some workloads will be pessimized. What to do here? At first, we can try to build several versions of your applications per workload. So if you have two distinct workloads, you can try to collect two distinct PGO profiles and then compile two different versions of your applications, deploy them, and route traffic between them based on some runtime criteria, something like that. If you cannot do it, you can try to collect multiple PGO profiles from multiple workloads, merge them into one. It's possible to perform via tools like LLVM Prof Data and use this one generic profile during the optimization phase. Yes, probably for per workload, the peak performance will be less, but still it's expected to get some performance benefits compared to baseline without PGO at all. PGO build is not reproducible. Reproducibility is a hot topic nowadays, since mostly due to security concerns. And PGO can make things worse here, since it's an additional input to our compiler. If you pass two different PGO profiles to your compiler, you will get two different binaries. And that's a problem. How can you resolve it? It's really simple. Just commit a PGO profile to VCS and use this profile during each build. And you will get a reproducible build once again, of course, if you have it right now. But if you do this, you can get another problem that is called profile skew problem. If you save a PGO profile and you don't update it, your application is not dead. It's evolving, new code is added, some existing code is changed, and so on. This code will not be covered by existing PGO profile. And this code will not be optimized. And during the time, the PGO optimization will be less efficient. How to resolve it? Just regenerate PGO profiles with some frequency. Each commit, each time, each day, each deploy, and so on. There are different strategies. It depends on your application, how actively you contribute into it, how dynamic your target workload is, and so on. Once again, you need to think about this process. And the last but not least one, in some cases, PGO cannot help to optimize your application further, especially if you are talking about already heavily optimized applications like FFmpeg with many manually written assembly and so on. In this case, congratulations, you found really good software where even based on runtime statistics, it's not possible to optimize your software further, but remember that your code can be changed, and probably new code will be less efficient than existing. And maybe for this new code, PGO will work fine. So even if it doesn't work for you for now, maybe give a try to PGO in a month or in a year or so. Probably it will work. How should I collect PGO profiles? Actually, there are different strategies about how and where you can collect them. But at first, please don't use unit tests for collecting PGO profiles for them, for your application. Why? The main aim for unit tests is testing your application in many cases. Most of these cases, at least from my experience, are corner cases. With PGO, you are trying to do a different thing. You're trying to optimize your application to a target workload, and your target workload is not a corner case workload. At least I hope so. So please don't use unit test. Collecting PGO from benchmarks can be a good idea, but it depends. It depends on how similar chosen by you benchmark is to your target workload. If they are similar enough, for example, ClickBench, benchmark suite for OLAP workloads is pretty good for OLAP databases. It can be used. But if the benchmark is really different from your target workload, it should be avoided. You can try to prepare some manually crafted training scenario. For example, a bash script where you run your application with different inputs in different scenarios and so on, and you can try to mimic your target workload in this manually crafted training scenario. Actually, this way is commonly used, especially for open source projects, but there are some caveats here too, unfortunately. If your target workload is dynamic and it can change during the time, you need to track it somehow and tweak your crafted scenario correspondingly. So you need somehow to monitor it. And the last one, you can try to collect PGO profiles directly from production. That's the reason why Google implemented sampling PGO, because they wanted to collect PGO profiles directly from production. And this option is a really great option, but once again, be careful, because if you want to do so, probably instrumentation PGO is not the best way, because overhead can be really huge and you cannot harm performance. You cannot, in all cases, harm performance directly on production. So please be careful. So there is no silver bullet here. Once again, it depends. If we will talk about more advanced ways to perform PGO optimization, there is an idea, a way about continuous PGO profile guide optimization. Google, once again, inside has a project that is called Google Wide Profiler, or GWP. This tool collects runtime statistics about all Google services. And then this statistics is saved to a database, pre-processed a little bit, and used in CI pipelines for performing sampling PGO optimization phase. That's how Google uses PGO inside. Unfortunately, this tool is closed source, and there is no open source solution yet to use. There are ideas to implement such a platform based on Grafana Pyroscope or Elastic Universal Profiling platforms. Unfortunately, nothing to try yet, it's just an idea and some discussions. What about current PGO states across programming languages? C and C++ have the maturest existing PGO implementations in the world, because Google contributed to them a lot and contributes. Rust, D, and actually other GCC or LLVM-based technologies should be almost the same as C++, but without the most advanced PGO techniques like context-sensitive PGO. Nothing too critical, and probably they will be implemented later. Go compiler official supports PGO since the last August, I guess. And unfortunately, PGO implementation in the Go compiler is too immature for now. As far as I remember, it can only do PGO optimized inlining and devirtualization decisions during the compilation phase. But Google knows how to implement PGO. They have a lot of experience, and they contribute a lot into the existing implementation. So maybe in a few years, the PGO implementation in the Go compiler will be really, really, really good. C# supports PGO. This feature is called dynamic PGO. Cannot say much here because I'm not C# engineer, fortunately. And you can you can read about this feature in the Microsoft documentation. It's pretty well, and in some other sources that I will share with you later. GraalVM, that's an ahead-of-time compiler. I talk about ahead-of-time compiler because PGO is a technology for IoT world. GraalVM supports PGO, but unfortunately not enough publicly available information about how the PGO implementation is efficient for real cases, not for synthetic benchmarks. Actually, I've asked many questions about the PGO implementation, but unfortunately, at some point, they stopped to answer my questions about PGO in the upstream. For some reason, I don't know why. If there is someone from GraalVM project, I found you. So about other languages and compilers, with huge probability, PGO will not be implemented in them because the proper implementation for PGO inside a compiler is not a simple thing to do for a compiler engineer. What about current PGO state across packages and software? Unfortunately, not many real applications support building with PGO in their build scripts for various reasons. They don't know about PGO, they don't believe in PGO, they don't want to spend or waste their time with PGO and so on. That's exactly the reason why OS distributions also don't use PGO for its software usually, because the maintainers don't want to waste their time on implementing PGO in the build scripts, and also there is a question about limited amount of resources in the CI pipelines in OS distributions, especially if we are talking about exotic architectures like MIPS or something like that. However, some OS distributions enable PGO for more packages, some performance-oriented OS distributions like Gentoo, Clear Linux, or Cache OS. So if you want to find an example about how PGO can be integrated into the package recipe, so we can take a look on them. And from my experience, highly likely web browsers, Chromium-based and Firefox and all derivatives from them, and compilers like GCC, Clang, and Rust-C will be optimized with PGO in your distribution. But if you want to be sure, you need to recheck a package recipe for a package. So as a rule of thumb, if you want to use a PGO optimized software, you need to rebuild this software on your machine with your PGO profile. What about good candidates for applying PGO on? Actually, it's any application with many branches inside, where a compiler can decide to make different decisions about inlining, loop roll-and-rolling, and so on. Compilers, interpreters, databases, different parsers, JSON, XML, protobuf, whatever. Even operating system and drivers can be optimized with PGO, and there are benchmarks for them. And of course, your application can be here too. If you want to know about more advanced optimizations that can help to optimize your software even after applying PGO on them, like post-link optimizers, LLVM Bolt, Google Propeller, Intel Thin Layout Optimizer, that is really open sourced a week ago, by the way. Maybe some ideas about preparing application-specific operating systems. When you run, for example, a PostgreSQL on a Linux kernel, you collect PGO profiles for Linux kernel, and then you build a specific version of the Linux kernel, especially for running PostgreSQL, for maximizing performance. It's a real thing. There are such benchmarks too. Or even if you want to use some fancy things like machine learning or AI, in compilers there are such techniques too. Even in LLVM, it's possible to use some kind of neural networks during the optimization phase for performing some machine learning-based inlining decisions, and many more academic things like Oculus. Sorry, not today, maybe next time. So I will be happy to talk about them after the talk. And so if you are interested in PGO, I can suggest you to go to my repository. That's the best source about PGO in the internet, because it's my source. I collected a lot of materials about PGO, benchmarks, current status across multiple languages, build systems, package managers. I discuss the common traps and mitigations for them, current state about post-link optimizers and so on. So you need to go to this repository and then probably to directly to the documentation of your compiler. If you want to share some experience about PGO with me, good or bad, you can contact me via email, Telegram, Discord, whatever, or after the talk. And if you liked my talk, please leave the feedback. And that's it. That's a good time for your questions. Thank you.
Thank you. So, everyone, please scan this QR code right now to leave your feedback. I hope the system will work. And while you are doing this, I will start with my first question as our conference host. And I do remember with the last interview between Lex Freeman and Guido van Rossum, author of the Python programming language, Lex asked Guido why compiler and profile-guided optimization are not enabled by default in Python. This is an amazing thing that can make our code 100 times faster. Why it is not enabled by default? And Guido's answer was quite counterintuitive. He replied that by optimizing some paths in our code, so-called hot paths, we can unintentionally de-optimize other paths. And since modern code bases, they are dynamic, like the path can change suddenly from hot to not so hot, the code, which is highly optimized, can suddenly start working slow, very slow, because it just switched to some cold path. So with this profile-guided optimization, did you experience any practical situation where profile-guided optimization resulted in code being not faster, but slower, because the profile which was recorded and the profile which was actually used became different?
Yes. That's actually a great question. Yes, I met a lot of examples where profile guide optimization pessimized performance, actually. There are different reasons for that. One of them I've talked about earlier. That's the nature of PGO. If you optimize one scenarios, in some cases, you need to pessimize others. That's an expected behavior. In my repository, I collected a lot of benchmarks, and actually you can recheck where and how much the performance was decreased after applying PGO. And just as a note, CPython, it's an interpreter for Python, is already PGO optimized in the build scripts and in all major distributions.
Yep. So let's listen to our audience.
Thank you very much for your talk. Can you elaborate more on security implications of PGO? Like, as an example, your first function, which triggered me a little bit, is called like is top secret value. And then we kind of optimize it for the good case, where we send it 42 and we get a faster result. That kind of inadvertently introduces like a side channel attack. So, for example, other options for PGO where I can mark my code, they if I use PGOs, that like this code should be constant time, for example, and I really don't want like PGO to touch it?
Yep. That's a good question. I would say that at first it depends on your threat model. So if you don't care about side channel attacks, so you just don't need to mitigate them. So about constant time execution, I would say you need to implement constant time execution, you need to implement some specific stuff inside your code, like timers inside, when measures how long did it take to execute some amount of code and introduce some pause in that. So with profile guide optimization, you should do exactly the same thing. So probably your good workload will be more efficient, it's a good part, just increase your timer. So my answer is the tooling to prevent side channel attacks should be exactly the same as you already have in your application, and it shouldn't be affected.
Please use the microphone again.
Like the typical constant time implementation would not include branches. So, for example, if I implement my code with branchless, can I be sure that like profile guide optimization will not influence?
You cannot be sure also if your regular code, because let's be honest, a compiler it's a black box. So if you are sure if your current code, you also should be sure if a PGO. There is a trick here, since modern compilers are pretty pessimistic about inline assembly. So if you want to disable some clever tricks in your compiler about optimization for specific part of your source code, just insert inline assembly. And inline assembly will not be PGO optimized, as far as I know, about any modern compiler.
As our partners in XNAS say, good enough sometimes is not good enough. And there are different kinds of optimizations. Of course, we have our profile-guided optimization, but we have other optimizations in our compilers that we can enable, disable, and some of them are mutually incompatible with profile-guided optimization, like we can enable some advanced optimization, which will do all the code optimization by themselves and not based on the profile. So, with your experience, did you encounter any good optimization that are mutually incompatible with profile guided, and where you need to choose? Do you want to apply the profile-guided optimization or some other compiler optimization options?
The answer will be a bit complicated in theory and in practice. In theory, I didn't find any incompatible with a PGO optimization. You can use it with architecture-specific optimization like March or Mtune. You can use it with user hints. You can use it with some O3, loop roll unrolling, and so on. It can be used. Practice, a bit different. I found a really annoying bug in the Rust C compiler when you cannot, for some applications, you cannot use at the same time link time optimization and profile guide optimization. The reason is simple, because the compiler crashes due to some internal LLVM error. This bug was reported many months ago, and unfortunately no one in the upstream cares about it. So probably it will be fixed somewhere, but for now there is such a limitation. I want to reassure you, you should use profile guide optimization is link time optimization by default. And only if it doesn't work for you for some reason, like undefined behavior in your application or compiler crashes, you need to disable PGO or LTO. Honestly, I recommend to start from LTO and only after that to enable PGO, simply because enabling LTO is a much more easier thing to do.
Our conference is called Tech Internals Conf, so deep insights into our technology are welcome. Any other questions from our audience? Yeah, because I can continue to interrogate him, and it's much better and easier for our speaker if you ask questions. Please.
Thank you. Thank you for great talk. Learned something new today, which is impressive. From your experience, can you share some expertise how well this transfers between different hardware? So let's say we did a PGO on AMD bare metal, and then we have a huge data center or data centers with mix of Intel, AMD, different architectures.
The answer is good for you. PGO is architecture-independent optimization, so it doesn't care actually about your target architecture. x86, 64, ARM, RISC-V, or whatever. PGO can be applied to any of them simply because PGO affects optimizations that are performed before generating the machine code. If you know something about LLVM internal architecture, there are three major parts: front end, that parses your source code; middle end, where major optimizations are performed; and back end, that generates machine code. Also, some optimizations are performed, like register spilling. So, and PGO at most affects optimizations on middle end, some inlining, hot code splitting, and so on. So it can be used on AMD, Intel, whatever you want.
That actually was my next question, proposed question, on what stage of the LLVM pipeline these optimization are applied, and are there any difference, like are there any cases where bytecode optimization done by LLVM before generating the machine code can be better if the profile-guided optimization is not applied? But you already did answer this question, so please, you're welcome.
Yeah, I wanted to ask him a question, but I just wanted to reconfirm. So technically, if I collect the profile on x86 machine, and because you said, for example, like the sampling is not very well supported on ARM, if I collect my profile on x86 machine and just compile my software for ARM64, that would still be working?
Yes. However, where is the caveat? If you have an architecture-specific source code inside, for example, that is behind ifdef or runtime CPU dispatch, if this code is not executed during the training workload, it will not be PGO optimized. From my experience, the amount of such a code is really low in our real applications, so it shouldn't be a huge deal. But if you have hot functions inside this part of your program and they are not PGO covered, so it can affect really much PGO performance in practice.
And my real question is, you briefly touched on about like how sensitive are profiles between software versions. So for example, to avoid the loop of like compiling my software, collecting the profile for production and recompiling, for example, can I like just collect the profile on the previous version of the software and then like when I compile the next version, just apply that profile?
Yes, you can. And as far as I remember, actually that's how recommended to use PGO profile in the official Go documentation about PGO.
That's a really great question. I like it, and I want to elaborate on it. Collecting this profile information normally takes time, and with our common software development cycle, we prefer fast CI/CD system. So software development can push something into the repository, CI/CD kicks in, and they have errors, tests, and so on as fast as possible. So with profile-guided optimization, we tend to have some separate, dedicated server that do all the profiles and compilation and so on, so the actual profile-optimized binary can be created hours and hours after the initial push. And this gives us this disparity that we want to run our tests and like degradation tests also toward binary, which is not profile-guided optimization, because we will receive this optimized profiler much later from the dedicated server. So from your experience, should we always run all the tests on the real profile-guided optimized binary and just wait, or it is a viable solution to compile fast without profiles, run tests, and apply all optimization on some slow, dedicated build system? What is your opinion on this topic?
So, as an architect, my answer is it depends. So actually it depends on many factors like your target, time to market, time, and so on. There are applications that are updated like once in a year or so. So you don't, in these cases, you don't have such a limitation. If you target really strict time to market requirements, there are different ways how you can try to mitigate it. At first, you can just buy a faster server for running PGO benchmarks. So the second one is you can try to tweak your training scenario, because in many cases, there is no reason to run a PGO training workload for hours. We don't care about how long did we run our PGO training scenario. We care about PGO coverage for our application. So if you can run your training, if you can prepare a small training scenario that can be completed for minutes, you can use it, and in many cases, it will be as efficient or almost as efficient as a PGO training workload that you will run, for example, for a week. So you need to perform some tweaks in your training scenarios.
Thank you, Alexander. Thank you. We are out of time, but not out of discussions. Of course, please one more round of applause to our speaker.